Okay, well, welcome, and thanks for taking a little bit of time to clarify what we did in class. And we'll take a look at simplifying some radicals, and we'll also look at how to apply that with the Pythagorean theorem for a moment. Um, so let's get cracking here. So remember in class, one of the things we talked about is that we want to break this down into things where we're kind of looking at pairs. So remember that we want to remember things like that the square root of 4 is 2, the square root of 9 is 3, and maybe the square root of 16 is 4. But remember, effectively, that's because the square root of 4 is 2 because the square root of 4, 2 squared is 4, right? And the square root of 2 squared, those are inverses of each other, so they cancel out. So a square root and a square cancel out. So really, in a sense, as long as we're looking for a square root, we want to find a square to perfectly balance that. And so sometimes you could look at these problems and see things very, very quickly. For example, in this first question, I did on purpose to make it fairly clear. I think everybody knows that 50 is 25 times 2, and we can very easily see that the square root of 25 is 5. So we could say that that is 5 root 2, right? So that's fairly simple. I can't do anything more with that, but sometimes you end up with problems that maybe you don't readily recognize. This is one of those numbers. 147 is beyond the value that exists in most of our multiplication tables that we learned as a kid. So we go through our kind of number sense thoughts. We know that this is not divisible by 2, and therefore 4 isn't going to work. We know that it's not divisible by 5, so like 25 isn't going to work. But there is a nice little trick that if you add up the digits, 1 plus 4 is 5, and 5 plus 7 is 12. And because the number 3 divides perfectly into the number 12, that means 3 is going to divide into 147. So if we made a nice little factor tree, we would find out that 3 times 49 is the number 147. So if we were to think of 147 as 49 times 3, I know that the square root of 49 is 7, and so we're good to go. Now, on smaller problems, that's how I personally like to do it. But when you get into the larger numbers, then what we can do is what we talked about in class, play and go fish. So if we're looking at 720, I'm going to go ahead and make a little factor tree out of it. And the first thing that I noticed is I've got 10 times 72, which of course is factor is down all the way to 2 times 5. And everybody's going to have their own way of doing this. But what I noticed is that I have 2 times 36. And again, remember, I'm looking for those perfect pairs anyway. And I noticed that 36 is 6 times 6. So if we're looking through this problem, what I notice right away is that I have a pair of 2's right here and here. I also noticed that I have a pair of 6's right here and here. Remember, we're looking all the way down to the end of those things. So we're looking at these values at the very end of the tree. And since I had a pair of 2's and I had a pair of 6's, this 5 right here was the one piece that was not left and that I didn't have a pair for. And so I got 12 roots of 5. Now, I will say for me, when I look at these kind of problems, I'm always like wanting to make sure that I am right. So one of the things that I personally like to do is ask my calculator what the square root of 720 is. And I got some nice little decimal, 26.8, right? Well, I thought that the answer right here was also 12 times the square root of 5. Well, let's see. Well, I also got 26.8. So that does tell me that at bare minimum, this is equivalent to what I started with. But even better yet, I know that the number 5 cannot be broken down further. So I'm done. Okay. So we'll do one more like that, 648. Designed this one on purpose to be pretty clearly divisible by 2. And in fact, we could probably go up a little bit. I'm going to go ahead and try to divide by 4. And so I got 4 times 162, which of course 4 is 2 times 2. I notice 162 is 2 times 81. And again, you could break it down to further pieces, but I'm going to go ahead and go 9 times 9. And again, I notice I have a pair of 2's and a pair of 9's. I've got a pair of 2's and a pair of 9's. That's what's going to go outside my radical. And then the only piece that is left sitting at the end here is the 2. So I got 18 roots of 2. So again, I want to double check that and look at what 18 roots of 2 is, and I got 25.45, and I want to make sure that the square root of 648 is that same value. So it was 25.45. So I feel like I did okay. Now, let's go ahead and talk about why would we want to simplify radicals in the context of a geometry class? Well, the Pythagorean theorem is obviously a very common thing to do in a geometry class. And so we've actually done the Pythagorean theorem, but so far we did it just with decimals. So remember the Pythagorean theorem says a squared plus b squared is c squared. So 4 squared plus 8 squared is c squared. That would be 16 plus 64. And 16 and 64 adds up to 80. So now we're ready to go. So C would be the square root of 80. So now it's time for me to start messing with it a little bit. So I noticed that clearly the number 80 is divisible by 10. But in fact, what I think I'm going to do, because I kind of done a problem like this before, I'm going to try just the number 5. And I know that 80 divided by 5 is a pretty nice number at 16. Now, remember, we're looking for pairs. Now, if you had picked 8 times 10, it'll work. You'll just break it down a little further before you see those smaller pairs. But I noticed that I got a pair of 4s. So I've got a 4 is my pair with a root 5 here. Perfect. So that I've got 4 roots of 5, okay? Now, on this one, I purposely put a root here because that's going to make things a little bit harder. So I've got a squared plus b squared equals c squared. Hopefully I have left myself enough room. But if I take 5 root 5 and I square it, well, 5 squared is 25, and root 5 squared is 5 because a square is an inverse of a square root. They just cancel each other out. So again, 5 squared is 25, root 5 squared is 5. And according to my calculator, 15 squared is 225. So looks like I got 25 times 5, which is 125, plus another 225. This part is 350. Okay. Now, again, I'm not totally sure what everything is, but I know that 350 is going to definitely be divisible. If you think about it, $3.50, you could totally make it out of quarters. So I know I could break 350 by 25. And so I've got 350 is 25 times 14. Now, 14, I could break it, but 2 and 7 is not going to have any kind of partnership, but 25 is as a pair of 5s. So kind of didn't lay this out very well, but the square root of 350 then is going to be equal to a pair of 5s, and what's left inside is both the 2 and the 7. So we usually just write that as root 14. But like I said, let's just double check that. If I took 5 root 5 and I squared that and I added it to 15 squared, I do get the 350 that I was hoping for. The square root of 350 is this decimal 18.7, and 5 square roots of 14 is also 18.7. Okay, 2 more and then we'll be done. Okay, so again, next one is that a squared plus b squared equals c squared. Now keep in mind that c always has to be the hypotenuse, which is the side across from that 90. No matter what we do, that c squared has to be the longest side. So I have 36 here. 12 times 12 is 144. We're going to go ahead and subtract 36 from both sides. And see, 144 minus 36 is 108. And we're going to see if we can break down the number 108. So again, clearly we know that 2 goes in there 54 times, and that jumps into a number that a lot of us are going to recognize as maybe 9 times 6. So if we kept going, that's 3 times 3 and 2 times 3. So as you go down the line through that particular problem and we start looking for pairs, this one is kind of interesting because we definitely have a pair of 3s here, but we also have a pair of 2s up here and a pair and a 2 right there. So all that's left is that 3. So the square root of 108, making sure I didn't write too low on my page, has a 3 in it, it has a 2 in it, and a root 3 is on the inside. So that's going to leave me with 6 roots of 3. Okay. Last one. Here we go. We're going to put a special root on the hypotenuse. So again, a squared plus b squared is c squared, where a is going to be one of the legs, b is the other leg, and c is the hypotenuse. So this time we're going to get that. So similar to a previous problem, 5 squared is 25. Root 2 squared right here is going to be 2. So I got x squared plus 16 equals 50. And so I got x squared is 34. So if x is root 34, I just have to go ahead and do a little teeny bit of work on root 34 to see what happens. I wish I'd given myself a little bit more room here, but no big. I'll just write it right here. 34 is divisible by 2. 2 goes in there 17 times. And that's a prime number. That's a prime number. I have no perfect squares. I have no pairs. I have nothing I can pull out. I guess root 34 is the end of my story. I will see you back in class. Hopefully that was helpful, remembering how to simplify radicals and apply that with the Pythagorean theorem. All right, have a good day. Bye-bye.